Hello, in this video I thought we'd take a look at a fundamental component of all 2D engines, the ability to transform your sprites. But before we get started, I'm just going to remind you about the One Lone Coder Code Jam 2018. If you haven't signed up, check the link below. It starts next week and that's when I'll be releasing the theme. And the theme of it is going to be...
Well, of course you're going to have to wait for that until next week. Anyway, we're going to be looking at rotating sprites. Well, not just rotating them, but providing all sorts of different types of transformations to sprites. So here I've got a sprite of a car, and I can rotate it. I can also change the scale of it in both axes. Let's make it a bit bigger again so we don't lose it. There we go. And I can do a shear transform as well. Shears are a bit weird. I don't know how useful they are, but they can be used for sort of wobbly effects. But certainly, the ability to rotate and position and scale sprites on a screen is really important.
And so in this video, I want to introduce the code to implement an affine transform. Let's get started.
For this video, I'm going to use the One Lone Coder Pixel Game Engine. And I've already created the bare bones of what's required here. I've overridden the Pixel Game Engine class with a base class called Sprite Transforms. And that'll provide two functions, onUserCreate and onUserUpdate. OnUserCreate is called once, and onUserUpdate is called every single frame. I'll create an instance of this derived class in my main function, and the size of the Pixel Game Engine window I'm creating is going to be 256 pixels by 240, where each pixel in Game Engine space is 4 by 4 pixels on my screen space. Since I started with the console game engine and now the Pixel game engine, the concept of a sprite has been quite fundamental. So I've added a variable called sprcar, it's a pointer to a type of sprite. And in onUserCreate, I'm going to load a PNG file into that sprite object. Drawing the sprite to the screen is quite a routine operation. Firstly, I'm going to clear the screen entirely to dark cyan in this case. It makes a change from black, makes the thumbnail a bit more interesting. And I'm going to draw the sprite to location 00, which is the top left, with a single one-line command, draw sprite. So that's it, that's our program. We're going to load the sprite and draw it to the screen, something we've done many times on this channel. And there we go. We can see the sprite of a yellow car with a white background on the dark cyan background of the Pixel Game Engine window. The car has a white background because we've not told the Pixel Game Engine to care about alpha blending the transparency of the PNG file. Now PNG files, they contain their own transparency information, but we choose not to use it in most cases because actually blending things together is quite computationally intensive, so you only want to do it when and where you need it. So just before I draw the sprite, I'm going to set the pixel mode to alpha, and that'll instruct the Pixel Game Engine to actually acknowledge that the pixels in the PNG file or the sprite have transparency. But it's important that once we've enabled it, we should also disable it as well, because here, if we didn't set these back to normal, the next time we call the clear screen function, it'll try to take into account all of the alpha values that are there too, which would slow things down. And just to sanity check that that works, there we go, we've now got the car without the white border.
So far so good. We can easily draw the sprite at any XY location on the screen, i.e. we can offset it or translate it anywhere we want. And in fact in the Pixel Game Engine we can go one further. We can integer scale the sprite too.
And this is very simply done. And by integer scaling, what I mean is we provide an integer value as the fourth argument of the drawSprite function, and it will modify, as we can see now, the car is twice as large. So it is scaled in both axes by a factor of 2. Change it to 3. And it's 3 times bigger.
And I can do integer scaling quite simply because the sprite shares its x and y axes with the x and y axes of the screen. In the example I've just shown, instead of drawing 1 pixel, I'll draw 3 pixels instead. Easy stuff. But this is not very applicable when you want to start rotating the sprites.
And we've done the rotation of a point many times on this channel, and so we should know these formulae off by heart now. But if we wanted to transform point x, we would take cos theta, which is how much we want to rotate it by, times x plus sine theta times y. And for the y component, it's very similar, minus sine theta x plus cos theta y. And so this will take our original x and y point, rotate it by theta, and produce a new x and y point. If you're interested in how this is derived, I suggest you go and check out the Code It Yourself Asteroids video. I do a full derivation there. Alongside rotation, we may also want translation, the ability to move the sprite somewhere along the plane. Well, we can see here that once we've rotated the point, we can offset it quite easily by adding another component. So let's say a translation in the x and a translation in the y. And depending on how you want to look at things, you could also take the whole lot and multiply it by a scaling factor, scale x or scale y. The order in which you do these things is of course important. One of the things I've done a lot of this year is transformation matrices. So here we've got the rotation matrix equivalent of the equations we've just seen and the scaling matrix. We don't have one for translation, and that's because we've not got enough dimensions here. If you remember, how we calculate matrices is quite a simple algorithm. We go along each row of the element on the left hand side of the multiplication and multiply it by the column on the right hand side. So this cos gets multiplied by this x cos theta, and we add to that this sine multiplied by this y plus y sine theta. And then we do the same for the bottom row, minus x sine theta plus y cos theta. And I'll just close off my matrix. These two equations are of course what we've just seen on the previous page, but you'll notice we need a third additional term to implement the translation. So let's just rewrite things a little bit. I'm going to extend the rotation matrix to accommodate the additional term. So it now becomes a 3 by 3 matrix. And when we do our multiplication, we're multiplying by x and by y and by 1. In this case, the third term would be 1 multiplied by 0, or 1 multiplied by 1. In either way, it's irrelevant. In fact, we'll do exactly the same for our scaling matrix. 0, 0, 1, 0, 0. So now our scaling matrix is also a 3 by 3 matrix. But now we have enough dimensions to create a translation matrix, which is 1, 0, tx, 0, 1, ty, because these are the terms that get added on, remember, and 0, 0, 1, just to make it a 3 by 3. And now that our three fundamental transforms are all 3 by 3 matrices, of course, we can combine them. So we could scale something, then rotate it, then translate it, then rotate it, then scale it, then translate it again, then scale something else, and we'll get a combined transform. The result of this combined transform is itself a 3 by 3 matrix, which means we can have a very complicated transformation represented with a little amount of data. And these sorts of combined transforms are called affine transforms. Affine transforms have lots of interesting mathematical properties in their own right, but I'm only interested in rotating and drawing sprites in different places. And as with a lot of programming algorithms, Wikipedia isn't a bad place to go. Yes, it starts to talk about the affine transform from quite a mathematical perspective, but what I like about the article is about 2/3 of the way down, we get to see it lists affine matrices as 3 by 3 matrices with an example of what they do. So here we've got the identity matrix, which does nothing. It keeps the image untransformed. We've got the reflection matrix. Well, if we look at the reflection matrix, we can actually see that that's the same as the scale matrix. We're only affecting things on the leading diagonal. In this case, we're multiplying our x value by -1, so we get a flip in the x-axis. That's no different to scaling, except we're using a minus sign in the front. We've also got, here we go, the rotation 3 by 3 matrix. Very nice, we've just seen that. And we have an odd one here, which is called shear, which allows us to sort of stretch along one axis only. And the thing to know about affine transforms is that parallel lines always remain parallel. So let's get started with implementing our own matrix framework. I'm going to remove what we've already got so far. I'm going to create a basic struct called matrix 3 by 3. It's just a 3 by 3 two-dimensional array of floating point numbers. And I'm going to adopt the convention that I'll do things column and then row. This is the same as x and y. Just as we did with the Code It Yourself 3D graphics series, I'm going to add some utility functions to help me work with these matrices. So the first function I'll add is a function that just simply sets the matrix that's passed into it to be an identity. The leading diagonals are set to 1. And we know that we're going to be multiplying matrices a lot, so I'm going to add a quick function just to do that. It simply loops through the columns and the rows and multiplies them accordingly. We also need a function to pass a point through our transformation matrix. So this is going to take in an x and a y value in the matrix and produce a new x and a y value after that point has been transformed. So you'll see here we've got the x coordinate multiplied by a matrix, the y coordinate multiplied by a matrix, but we don't have the z coordinate. I'm going to assume it's 1, so we're just going to accumulate the matrix. The humble draw sprite routine is no longer any good to us now. We'll have to create our own to use the transformation matrix. So I'm going to make an assumption that we'll have a final transformation. I'll call that mat final. And just to be on the safe side right now, I'll just make that an identity matrix. To perform the transformation, I'm going to take a really naive approach. And it's not going to be the approach we'll finish with, but I think it shows an interesting concept on the journey. I'm going to create 2 for loops that will allow me to iterate across each pixel contained within the sprite. And I'm going to sample that pixel and store it in this value p here. 2 additional floating point variables are going to represent my new x and new y coordinate after I have transformed the x and y coordinate from sprite space. So this will put it into screen space. And this is just a matter of calling the forward function we've just defined. Once we've got the new x and the new y function, we then draw the pixel using the standard Pixel Game Engine draw function in the new location. So we've taken the point within the sprite, transformed it, and we're drawing it to the transform location on the screen. Now, because this is an identity matrix, what we should see is no difference at all. Let's take a look. Perfect. What we see is the car aligned with the top left. So let's add a translation matrix. We want to move the sprite around on the screen. Well, that's just a case of setting this value and this value in the rightmost column. And instead of calling the identity function, let's call the translate function. And we'll pass into that a value, 100 by 100. So this should offset the sprite from the top left somewhere towards the middle of the screen. Let's take a look. And very nice, it has done. So our translation effect has worked quite nicely, and we've used matrices to do this. I'll go ahead and simply add in the 3 other types of affine transform matrix: rotation, scaling, and shear. Let's try them out. So let's say I wanted to draw the sprite half the size it should be. Well, I'll apply scaling factors of 0.5 to both axes. Let's take a look at that. Well, the car seems smaller, and quite nicely, it's not got any awkward artifacts there to complain about. Good. Let's make it larger. We'll make it twice as large, so we'll have a scaling factor of 2 in both axes. Let's take a look now. Yes.
We seem to have hit a bit of a snag here. There's gaps throughout the image. Why is this? Well, simply we've not got enough pixels. As we've iterated through all of the pixels in the sprites, we've created new locations for those pixels, but there are gaps in between them. We'll have a look at filling these gaps in a bit, but let's try the other transforms first.
Well, scale was a bit unsuccessful, so let's try rotate instead. And we'll rotate by some arbitrary amount, 0.2. This is of course in radians. Well, it certainly rotated the image, but there are those pesky blank pixels again. Nonetheless, let's try some combined transformations as well. I'm going to need some more matrices for these. Just some temporary ones. At the moment, we've just rotated the sprite around its top left coordinate. Let's rotate it around the middle. So this means we'll need to translate the sprite before we do any rotation. So let's create a translation matrix to do that. We'll store that in mat A. Now I happen to know that the sprite is 200 pixels wide by 100 pixels high. So if I translate it by -100 and -50, I'll move the 0 point to the middle of the sprite. I still want to do the rotation, but I'm going to store that in matrix B. And so I want to combine these 2 matrices into my matrix final. I'll call the matrix multiply function that we created earlier. The order of operations here is quite important. Let's see if we've got it right. Well, I'm looking at that and thinking, no, we didn't get it quite right. Let's reverse those around. Okay, that's looking a little bit more sensible. Certainly the middle of the roof of the car is now top left, and it's angled. So we probably want to offset the car now to the middle of the screen. This means we need another translation operation. I'll reuse matrix A now we're done with it, and I will set the translation to be screen width divided by 2 and screen height divided by 2. Make sure I put this matrix multiply in the right place first. So we've done the translation and rotation, and that's given us mat final. Then we're creating another matrix A. I'm going to need some more matrices here, aren't I? Let's add in a mat C. So instead of translating to the final, we'll go to mat C first. And now our final multiply will give us the final matrix. We've got our new translation going in, and we want to multiply that with what we had previously. It's getting a bit complicated, this. And there we go. We can see the car now offset to the middle, nicely bang on in the middle, and rotated by a certain amount. Let's just test this rotation. I'll add in some keystrokes to handle some user presses to rotate the car. We'll need a quick variable. I'll call this one fRotate, and I'll just initialize it to 0. And I'm going to be sensitive to the Z and X keys to increase or decrease that value as necessary. I'll use felapse time so it's nice and smooth. So instead of this hard-coded value, let's put in our rotate value. We'll come back to this sort of matrix mess in a minute. Let's just see if this works. So that looks like the car normally. I'm going to start rotating it, and it does rotate. We've still got these pesky cyan dots all over the place, but it seems to be doing quite a nice and smooth rotation. And certainly the performance is quite good too. That's a pretty funky pattern. The reason the matrix stuff gets a little bit complicated is matrix multiplication is not commutative, i.e. the order matters. And that's why we saw at the start I had to switch around the A and B values. So I created two exclusive matrices, one to translate and one to rotate. And I've multiplied them in the correct order to give me a new matrix, matrix C. I then want to take matrix C as my already existing matrix and multiply it by a new matrix which represents a translation to the middle of the screen. What is it we've just done here? Well, without any transformation, we saw the sprite was drawn on the screen in the top left. And that's because the sprite's top left was aligned with the screen's top left. The first translation operation translated the car sprite so that the middle of the sprite was aligned with the top left of the screen, i.e. we moved the origin of the sprite to its middle. The origin being in the middle of the sprite is quite useful for scaling and rotation, because we'll always rotate around the origin. And so in this case, that's exactly what we did. Sprite doesn't quite fit on my screen here. And once we've rotated the sprite, we then translated it back to the middle of the screen.
So what can we do about these annoying gaps in our sprite?
In the source sprite, marked here in blue, we're iterating across our pixels one by one. This means our transformed image will only ever consist of the same number of pixels. But the locations of these pixels may not align very nicely with the pixels on the screen, and so we start to see the gaps in between. We saw this especially when we were scaling. I think that's a very visual example of this effect. And so the problem has come around because of the forward way we're doing things. I'm going to suggest doing things backwards. So firstly, we'll work out the area that our sprite is going to occupy once it's transformed. I'll have some sort of bounding box. We know that we'll cover every single pixel of the sprite within this region. And instead of projecting the source sprite to the destination sprite, I'm now going to iterate through the bounding box pixels, which I know are now aligned with the screen, and sample from the correct location in the image. In effect, what we want is the transform that takes our final sprite location, rotation, scale and shear and gives us the original sprite location, rotation, scale and shear. We want the inverse of the transform we actually created to begin with.
Now we know that this approach will leave no gaps because we're going to go across all of the pixels in that region. But this does require a matrix inversion. And as I've said in the past, Matrix inversion is a very complicated field, and it's well beyond my skill to be able to explain nicely. So I'm just going to take an off-the-shelf 3x3 matrix inversion function and manipulate it to our needs.
And so, blam, there we go. And it looks horrific, and indeed it is horrific. But what I should point out is it's nothing more than multiplies and additions. Subtraction and addition are pretty much the same thing. So even though there's a lot to do, it's actually quite simple for a CPU, which is optimized for doing things like multiplications and additions. It's also important to note that we're not going to need to do this for every pixel, just once the transform is established. Once we've got the correct transformation matrix, or in this case the inverted transformation matrix, then we just pass points through it using our forward function as normal. So in many respects, I tend to treat things like this as a non-recurrent expenditure.
And I'll also add, I've made no attempt to optimize any of this at all. I want to just keep it clear, as I did with the 3D graphics engine.
So knowing that we're going to need an additional matrix, let's quickly add it. Matrix final inv, and we'll calculate the inverse matrix right here. Invert mat final inv. Now, I've not changed the drawing function just yet because we've got one last problem to solve. I'll just quickly run this again. And what it is how do we work out where the bounding box of our sprite is? Well, one assumption we can make is that the corners of our sprite are accurately projected in space. And so if we pass through the coordinates of the corners of our sprite through our forward travelling matrix, i.e. the non-inverted one, we'll get some screen coordinates, which we can use to determine the bounding box. The way that we were originally drawing the sprite is now inaccurate, so I'm going to comment that out. We don't need it anymore. Instead, I want to work out where the bounding box of the transformed sprite is going to be. And so to do this, I'm going to pass through each corner of the existing sprite forward through the transformation to work out where the bounding box is. And so I've created four variables, start x and start y, and end x and end y. They'll give us the four sides of our bounding rectangle. I'm going to create two additional variables, px and py. You'll see why in a minute. So taking the top left of the sprite, which would be 0, 0, I can pass that through our forward function using our standard transformation matrix. There's the 0, 0, and the result is going to be placed into px and py. Well, to start with, that's all the information I have, so I'm going to set my starting x and y and ending x and y positions to be px and py. I'm then going to send through, in the forward direction, the opposite corner of our sprite. So this is like the full bottom right location of the sprite, the width and the height. Again, this goes through the normal matrix. Now ultimately I want to traverse through the bounding box from the top left of the bounding box to the bottom right. So I want to sort my starting x and y positions, which I do here. So for my starting x is always going to be the minimum of the point that we've just calculated, or the existing starting x location. And likewise, the ending x location is always going to be the maximum of my most recently calculated point, or what I've already got. The same happens for y. So now I've got the top left and bottom right of my bounding box. You might think that would be enough, but not when you've considered you've got rotations. We actually need to do all four locations of the sprite. So here is the bottom left, and here is the top right. So this algorithm will give me the bounding box of my transformed sprite, and I've needed the forward transformation matrix in order to do that. Now that I have the bounding box, I can now traverse through each pixel of the bounding box and use the inverse transformation to sample the sprite at the correct location. So all of the pixels in the bounding box are going to get selected. I'm not going to have any gaps. And the code looks very similar to what we had before. I'll use my forward command, but I'll use the inverted matrix to give me two new locations, and I'll use these locations to sample the sprite at a particular point. I've offset nx and ny because these are no longer integer. By adding 0.5 to them, I make sure that I'm rounding to the correct pixel. And so I guess the final thing to do is to draw the new pixel in the x and y location on the screen. So let's take a look. Well, the sprite looks good, but we've got no gaps, but we've not rotated anything yet. So let's start to rotate, and we can see nicely now that the bounding box is expanding and contracting as required. That might be useful for other things. But what we see is no gaps at all. In fact, it looks very nice. I like the fact that it bounces. It's very jolly. I think the last thing I'm going to do is enable alpha blending again for the sprite as we're drawing it. But I'll just take this bit of code and move it down here so we disable when we're clearing the screen. There we go. And so there you have it. We've got a sprite that has been transformed on the screen. It's been translated, it's been scaled, it's been rotated. We've looked at shears, but I don't think we'll ever use them for anything. That's quite a nice flexible routine for handling sprites.
In fact, I like it so much that I've wrapped it up in what has become the first Pixel Game Engine extension.
I'll now quickly prepare the program we've just written to use the extension. And this is a bit brutal. We're going to delete pretty much everything we've created. All I've left in is loading of a sprite, handling of the rotation, and the alpha mode settings. To use an extension for the Pixel Game Engine, after you've included OLC Pixel Game Engine.h, you can just include the extension. That's all you'll need to do. In this case, it's Graphics 2D. The extension provides several interfaces, one of which is OLC GFX 2D Transform 2D. So I'll create an instance of that. And just as we've done manually, we'll first, to this transform, we will translate it. We'll then rotate it to our rotate variable, and we'll translate it again to the middle of the screen. You'll notice I'm not needing to deal with matrices or matrix multiplication. That's all hidden behind the scenes, and it's written in a way that optimizes the creation and manipulation of matrix data. The final thing to do is to call another draw sprite routine. However, this one exists within the namespace of Graphics 2D. It's a special one because instead of taking coordinates, it takes the transform object we've just created. Let's take a look. And as you can see, it has exactly the same performance and behaviour as the manual code, but is considerably more concise. In fact, that's the entire program.
I quite like the idea of having extensions for the Pixel Game Engine, so I think I'll probably develop some more. And the interface is written in such a way that you guys can also create them quite easily too. I know some people on the Discord have already been working on controller interfaces, which I think is quite cool. Anyway, I've got a plan for being able to rotate sprites. Given we're approaching the end of the year, it's usually about this time I start having a think about a big project to do in the run-up to Christmas. So watch this space. Also, don't forget to take part in the jam if you're interested in doing so. The theme will be announced next Friday, that's the 16th. If you've liked this video, as usual, big thumbs up please. Have a think about subscribing, and I'll see you next time. Take care.